Okay, so why don't we going to get started? Welcome to today's DTech NYC seminar. For those who are new or not on the mailing list, you can go to this URL right here, bit.ly/DTech NYC, and sign up, and then you'll get the announcements for future speakers. Today, I'm really happy to introduce Bonnie John. Bonnie is a real esteemed member of the Human-Computer Interaction community. She's a member of the ACM Sig Chi Academy, which is the highest honor for researchers in the field. But I have a long relationship with Bonnie in that when I was a graduate student at Carnegie Mellon doing my PhD, she was one of my professors. In fact, I TA'd for her in the first human-computer interaction class I ever took even, did any, and it had a big influence on the way I teach to this day for this course. Bonnie's got an interesting background. She's native of New York City. Did an undergraduate in engineering mechanical
engineering.
Cooper Union,
Yep.
And then a master's in mechanical engineering at Stanford. And she really had this vision of how can we bring kind of engineering to human-computer interaction and engineering methods. And she went on and did her PhD at Carnegie Mellon, working with really some of the most famous people in the field, Herb Simon and Alan Newell and others, and then became a faculty member there, where she spent most of her career until she decided she would love to spend the rest of her career here in New York City, and has moved here and is now working at IBM Research. And so we're lucky to have her today. So without further ado,
thanks, James. Yes, I remember James's thesis when he would do user tests in the user studies lab that I ran, and he'd do one and everything would break. And then he would cancel all his appointments and program a lot until it worked again 2 days later, and then do it again. And that was, so James and I go back a long way. So just to give you a little bit more background on me before I started on this, after I graduated from Cooper Union, I got a job with Bell Laboratories, which at that point, before the breakup of the Bell system, was like the cool place to work at the time, okay? And they sent me away to get a master's degree at Stanford. And when I came back, I was a mechanical engineer and discovered that in the Bell system, mechanical engineers basically designed boxes around other people's circuits. So it was all heat flow and stuff, but, you know, it was kind of boring. So I quickly moved into systems engineering, where I was writing the 500-page specifications for data and telecommunication systems. And as I was writing these things, I was speccing things that people were going to use. And I started asking, well, is what I'm speccing going to be easy for people to use? And so, you know, I knew nothing about psychology, so I started taking psychology courses at night. And I discovered that psychology courses were not the same as my mechanical engineering courses. Because in mechanical engineering, you get these big, thick textbooks, and at the end of every chapter are problem sets. And so you have problems, and then at the back of the book, you have the answers to the problems. Because there was a way to do it, okay? And you could actually write down what a reasonable answer was, or what a set of reasonable answers were. But in psychology, there were no problems at the end of the chapters. There were names and dates and results. And so the name was who did the experiment. The date was what year did they do the experiment. And the result, of course, was what was the result of the experiment. But there was very little theory that let you predict what the result of the next experiment would be. But I was in system design, and every single design is an experiment. We are predicting that people will be better off using what we're designing now than using what they had before. And so I needed a way as an engineer to be able to predict what people were going to do on the next thing. And psychology was not in a shape to do that. So I quit my high-paying engineering job and went to be a slave, otherwise known as a psychology PhD student, and took my, 4.5, 5 years of getting that PhD to beat psychology into a form that engineers can use. And that has kind of been my bumper sticker or my mantra: beat psychology into a form that engineers can use. So I do something called predictive human performance modeling. But I have discovered over the years that if you call a class predictive human performance modeling for user interface design, you get 7 people signing up. If you call it cognitive crash dummies, you get 40 people signing up. Same course description. So marketing matters, all right? So I now call these things cognitive crash dummies. So what is a cognitive crash dummy? By analogy to a automotive crash dummy is a physical model that the automotive industry puts in their prototypes of cars and smashes them against walls to find out how much they're going to maim and kill people before they tool up to do the whole production of a car. So in that same way, a cognitive crash dummy is a way to evaluate design ideas before you implement them. And the way we do that is we have a computer-based computational model that mimics human behavior. So it is mimicking perception, cognition, and motor actions. Someday it may be able to mimic emotions and fear and the effects of fatigue and things like that, and people are working on that sort of thing in research. These are written in what's called a computational cognitive architecture, which you can think of as a programming language that has constraints on it so that you can only program in what people can do. And that's not quite true. You can write really bad models in these cognitive architectures, but if you do it the way they suggest that you do it, just like you can write really bad programs, you can get these cognitive architecture constraints on things like how fast does simulated time go? Okay, how fast does it take to think a thought? How fast does it take to move a hand from here to there? Those sorts of constraints are built into a cognitive architecture, and there's several of these. So they're giving the structure of memory and processors and how these things communicate with each other. They're giving you this programming language and some sort of IDE also to work in them, to express the knowledge that you expect people to have and what they can do. So then when a model in one of these architectures runs, it can give you predictions, it gives you a trace, and from that trace you can extract things like how long did it take to do that task in simulated time. You have a simulated human, you have your simulated user interface, doesn't have to work yet, okay? And then you, things like how many errors is it going to make, what kinds of errors is it going to make. There's some like Aptar that you could actually flip a switch flag and say, tell me what the blood oxygen level in different parts of the brain is going to be. So they can even predict that, okay? And then scientists go and compare these predictions to human behavior so that we can have confidence as designers that when we run our models, they will be accurate for us to predict whether our designs are going to be good. And so there are people in psychology departments and research in human-computer interaction that have been doing this for a long time, and so now we actually have some tools that can be used without having to have a PhD in psychology, without doing the psychology data collection, without building something first to tweak parameters. We can do things ahead of time. So I do call these cognitive crash dummies, and I have this lovely picture that a wonderful artist in Australia has created and given me permission to use however I want. This guy is using his information technology as he's driving down the road. He is doing it in Australia because it's on the wrong side of the road, right, for US, so don't worry, he's not driving it here. But there tend to be three uses for these type of human performance models. One is to predict what's going to happen on something before you implemented it, okay? One is to have a model of the user running alongside of actual data collection from the user, and then you can compare those and see if your actual human user is deviating from what way an ideal user or some sort of user that you expect to have might do. And these are very, very effective in what's called cognitive tutoring systems. So it's for educational purposes. You have an ideal student model that runs alongside of an individual student model that you're getting in real time. You can compare the two and see what would the ideal student know at this point, and what evidence do we have that the current student, the human student, has at this point. And when there's a mismatch, you give the human student more practice in the things that they are not knowing. A very, very highly successful. Hundreds of thousands of US students today learn algebra, geometry, and other math and programming from cognitive tutors built on this type of system. And then they could also substitute for human participants in collaborative or combative training situations, and you can imagine the military uses these. They have war games that, 50,000 entities, only 1,000 of them are people. Okay, and these types of models can be used there to give keep preparedness up for our armed forces and others. You can do it with medical and things like that as well. What we're going to talk about today is just the predicting the behavior on proposed design before implementing it. So very brief history of this is it's been around since the early 80s. So there was a book called The Psychology of Human-Computer Interaction by Stu Card, Tom Moran, and Alan Newell. Stu and Tom worked for Xerox PARC. Alan Newell had been their PhD advisor. He was at Carnegie Mellon. He was my PhD advisor as well, and I started the year this book came out. So this book actually was the book that coined the name of the field, human-computer interaction. Okay, and they presented modeling frameworks for doing these predictive models. They also have a whole, if you read the foreword to this book, they're talking about engineering models of human performance. And when I read the foreword of this book, after I had chosen to go to Carnegie Mellon and I was looking for an advisor, I read this and I said, oh, this is a match made in heaven. So I walked across that green grass called the quad, away from the psychology department to the computer science department, and said to Alan Newell, I think we need to work together, and he said, yes, we do. So I continued working on these engineering models that he had started. So what is this engineering model or cognitive crash dummy? It has to be able to produce a priori quantitative predictions. Most psychology models, a lot of them do what's called split half. So they collect a whole bunch of data, and they take the first half of it, they split it in half, they take one half and use it to set parameters on their model. And then they use those parameters to predict the second half of the data. Okay, that's too late for design. You don't want to build something to get parameters so that you can use a model. If you built it, you can do user testing. Okay, so you want to have something that can make a priori predictions, predictions based on prior research that have nothing to do with your design. And so you have to be able to make these quantitative predictions as well. People need to be able to speak in the same language. Usually that's dollars and cents. As a systems engineer, I would sit at a table where we were deciding about the specifications, and we'd sit with the engineers and with the human factors people, the applied psychologists, and we'd say, well, what are we going to put in the spec? And the human factors people would say, well, we like interface A better than interface B. But then the coding people would say, oh, that interface is going to take a lot more memory for me to put that interface in code. And the electrical engineers are going to say, oh, but then we need another chip. And then the mechanical engineers say, oh, but then the box has to be bigger. Okay, and they could all talk in terms of how many dollars this was going to be to the final cost of the design. And the human factors people pretty much only had opinion. We like this versus that. Cognitive crash dummies allow you to say things, but this is going to take someone half the amount of time to learn, and so you're going to save on training costs this many dollars. Or this is going to cause these many fewer errors, and so we're going to save money on our help, our call-in help. Or this is going to be a lot more efficient, so our end users, our companies that buy our stuff are going to be able to get their job done in half the amount of time. Okay, so everybody gets down to dollars and cents, so that's why it has to be quantitative. Also, not every company is big enough to have PhD psychologists roaming around doing this stuff. So the modeling has to be learnable and usable by system designers. So it can be computer scientists, it could be user experience designers who usually haven't taken a math class since high school, or often haven't taken a math class since high school, so it can't be very mathematical, can't require a PhD in psychology. Okay? And it has to cover total tasks. In psychology research, typically you'll have a model of reading, or a model of visual search, or a model of hand movement, or a model of typing, or a model of decision making. And they don't talk to each other. But when someone comes to do something on your computer or pulls out their smartphone, they're doing all of that. And so the models have to cover all of it, everything people do when they come to an interface. Usually when I give this talk in a psychology department, I see the professors going, this is impossible. Impossible. Okay? But that's why I have this last line. It only has to be usefully approximate. So scientists usually are going for the small effects. They want to make sure that they've gotten as close to the truth as possible. Engineers are perfectly happy with the 80-20 rule. Okay? Get me 80% accuracy with 20% of the effort, I'm happy. Okay, so you have to know how accurate it will be. When I talk to mechanical engineering audiences, I say, there are 32 terms in the Bernoulli equation, but most people only use the first 3. Okay, but you know what you're giving up by not using those other 29. Okay, so we do need to know how accurate these things are, but it doesn't have to be the truth, as much of the truth as the scientists want. I'm very happy the scientists continue and get closer to the truth, because then I can build it in underneath my engineering tools, but I only need it to be usefully approximate. So what can we do? Right now, we can predict the efficiency of interactive systems to within about 10% of the truth. We have been doing this in the field for 30 years. It's called the keystroke level model. It was in that book, Human Computer Interaction. And basically the procedure is to express what someone would have to do to accomplish a task that they know how to do. They're not problem solving. They know how to do it. Like, you know how to read your email. Okay? You know how to use your word processor. Okay? You express the actions that they would have to take in a small number of operators. Keystrokes, this was for desktop, pointing with a mouse, but it also works pointing with your finger. Okay? Homing between devices, so you have to go from your keyboard to your mouse. How much do you have to wait for the system? And this thing called a mental operator. Now, mental operators are a black box set by empirical research done a long time ago, but still holds up. It takes someone about a second to, people tend to pause at certain times for about a second. There's heuristics for placing them, and that's that other line. There are empirically established heuristics that they have to do with things like before someone issues a command, before they submit a whole stream of information, they want to make sure it's right so they go back and check it. And what they have found is that this black box of a mental operator with the heuristics that Carden, Rand, and Newell gave us back in the 1980s gets us within about 10% of the truth. And all you have to do is list these out, give empirically established time, like what is their typing speed. Pointing is a very well-known time called Fitts law, actually. And you just add them up. So the input would be a suite of tasks that you want to say these are important for it to be efficient, and a specification of the proposed system. It doesn't have to work. It could be just, sketches, okay? And what it gives you is the time it takes a skilled user to perform that task, or those tasks, on the proposed interface, or propose different ideas. So simple as this sounds, it was perceived to be too hard to learn and use by UX designers and developers. And I taught this for many years. I believe James probably taught keystroke level model as well. Did you?
I thought keystroke and COM.
Okay.
I never had them do it.
I didn't have them do it. Too hard to do it, yes. Okay, so I took this as a challenge because the theory works and experts can do it. So guess what? It's now an HCI problem, right? Now we just have to make an interface that brings this theory to people who don't have the knowledge and experience. So I created something called CogTool, which is an open source tool. This is when I was at Carnegie Mellon, okay, where designers can describe a design in a storyboard. And this is the language, when I went out and did all those HCI techniques that people tell you to do. I went out and did field work with UX designers and computer scientists. We found out what their languages are. Everybody likes storyboards. Everybody works in storyboards. So each one of these things, so each one of these guys is what the screen looks like. I'm sorry you can't see it very well, but so the screen looks like in a particular interface. And you draw hot spots on top of the screen. Now this can be a screenshot or Photoshop or just a sketch, okay? And you draw a little hot spot that says, oh, what someone would have to do is click on this, and then it would take them to the next screen. Okay, then they click on this and it would take them to the next screen. Or they type in something off the keyboard and it would take them to the next screen. Okay, so you build your storyboard as screens and transitions between the screens. And then you demonstrate a task, as many tasks as you want, on your storyboard. Now, these can get very squirrely. They can be big graphs. Storyboards can go off in lots of different directions. So you have to tell it what order do you do this task in. And when you get into this window, it brings up the first storyboard, it's the one you tell to start on, the first screen. And then you just do the things. You click around on those hotspots you made. And it is watching you. It's not timing you. So you could start this, go off and get a cup of coffee and come back, because what it's going to do is create a valid cognitive model that's going to run as a simulated human. And so it's not a user test where it's timing you. It's going to create a model. This is fabulous for some things. So for instance, if you're going to do a competitive analysis, and you have limited knowledge of exactly how your competitor's tool works, but you can get that, free 30-day trial period, you can capture screenshots and then go frantically looking through the PDF that says what I'm supposed to do next. And it doesn't matter how long it takes you to figure out what to do, because the model is going to be of a skilled person, of someone who knows how to do this task. So it's creating this model, and the things in white are the things that you actually do, like left click, but the things in yellow are the things that Consul puts in for you, creating this valid cognitive model. So it puts in where those think times are, that mental operator that I talked about, and it puts in things that keeps track of where the mouse is and how far you're moving and where your hands are and all that sort of stuff. So all you have to do is know how to do the task. And you don't even have to really know. You can go looking through documentation. Then you hit the compute button at the bottom, and you get a spreadsheet-like thing that gives you the different designs you're looking at in columns and the different tasks you're looking at in rows. And you could also do tasks in different ways. So like this one does it the same task using the keyboard as much as possible, and this one uses the mouse as much as possible. And you can see that you get different times for that. But even better than that, you can open up its head, because it's a model. It's not a person. And you can't go back and say, why did you do this? Why is it taking longer? So you can open up its head, and we have a visualization that shows you what's going on. So the top line is what the system is doing, stepping through that, those screenshots. The purplish is what the eyes are doing, where the eyes are moving around and perceiving information. The gray in the center is the cognition. It is those mental operators. Those are kind of big, long ones, but there's a lot of cognition that has to do with making the eyes do the right thing and making the hands do the right thing as well. And then the red is the right hand and left hand. And so here, this is a pattern that has to do with typing. Lots of rapid stuff happening hand to hand. This is more pointing and clicking. Okay, so that's the tool, and we have been using it at IBM. So, what time? I know we've spent a lot of time with tech. Oh, fabulous. Okay, great. So I can play my my little video. This is how we kind of try to sell this to software engineers who do specs and use cases and things like that. So let me just, it's only 3 minutes. Okay, we call that our marketing video. But it really does allow us this engineering approach of having quantitative requirements, being able to tell early whether we're going to meet those requirements or not, and even test. Okay, so this is a direction that we're going. But then you might be asking, why should anybody care about a few seconds? A few seconds here, a few seconds there. Well, there have been examples, and there will always be examples. And it may not be exactly what you're working on now, but you might come across it. So, for instance, I worked with Dynex, who wanted to invest $160 million purchasing a new workstation. I did the modeling that showed them that this would have cost them operating expenses about $2 million a year. They thought it was going to pay itself back in being more productive. And with the models, you can show why. They actually did an empirical test, and we predicted the result of the empirical test within 6%, but the empirical test couldn't tell them why. What was the problem with the design of this new workstation, and where the models could show where the design decisions had led them astray. There was a similar analysis done on the Tomahawk missiles, which showed that they would not be able to be armed in the amount of time they needed to be armed in. The analysis was given to the Navy. It was done by Navy people. It was given to the higher-ups in the Navy, and they didn't like that answer. So they ignored it. They built the system as designed, and it failed its acceptance test. That caused the taxpayers a lot of money. So when they investigated why it failed its acceptance test, they made a recommendation to do these types of models on every system. Okay. The next-gen airspace that you may have heard about, they're going to have economic consequences of not doing things fast enough in the cockpit. So if the air traffic controller tells the pilot to take a different route, and the pilot and the system cannot get that in fast enough in a little window of time, and they're going to miss that first waypoint, then they get relegated to a less desirable route, which is going to cost the airlines money in fuel, because that less desirable route will use more fuel. So a couple of seconds make a difference. Carlsbad Police did these sorts of analysis on their in-vehicle information system, because people have to take their eyes off the road to use this. Their police officers have to do this, and they credit it with saving lives. They reduced the number of accidents of the police officers who were driving to a call trying to get information on their information device. Okay. The SAE, which is the Society of Automotive Engineers, makes this a recommended practice for designing in-vehicle information systems. And this one that got IBM's attention was that they lost a $700 million contract to AT&T, because even though AT&T's system was $1.4 billion, twice as much as IBM's proposal, this analysis, plus a couple of others, showed that it was a better value for the U.S. taxpayer. So, yes, people do care about every little second. Maybe not on your smartphone, but there are other things that people design in the world.
Who did that?
Who did what? The IBM? Me.
So you did it as a consultant for IRS? Or for
I was hired by AT&T, who was working with the IRS to defend their choice. I can tell you that you know what I do, okay? I can tell you that AT&T let me testify, but I cannot tell you more than that, okay? But I can tell you that the redacted opinion says that this analysis, plus a couple of others, they had several other quantitative analyses, contributed to the defense of spending the taxpayers' money that way. Yeah, and that did get AT&T upper management's attention to one of the reasons they hired me. Okay, so yes, skilled performance time does make a difference, but it's not just skilled performance time. We can do some analyses of novices as well. So you swap out that model under the hood of a skilled person, and you stick in one of a novice human. So there's a system called Cog2 Explorer, which was Liang Weitao's CMU PhD. It has a model of what's called information foraging, which is a psychological model expressed in a computational cognitive architecture called ACT-R of how people search for information. So we took out the skilled model and stuck in information foraging under the hood now. So now you give it the same storyboard, but instead of telling it how to do the task, you just give it a goal. And so you type in a little sentence or paragraph about what the goal is, and then you say go. Or you say this is the start screen, this is your goal, go. And it uses this model of novice humans under the hood to start clicking on stuff. Okay? And so what you get is predictions of novice behavior. So it's looking around the screen, and it may click on the wrong thing. And it's got a lot of math under the hood to decide whether the utility of reading the next link is higher than the utility of clicking on something I've seen so far, is higher than the utility of backing up and going to the previous screen. Okay, so it's doing a lot of math underneath. And this is what it kind of looks like. So it starts at the upper left corner. It looks at the link nearest in this, because it has a model of eyes and how eyes move around. Okay, and it evaluates this link or button to say, what's the information sent of this relative to my goal? An information sent is actually a quantity that says how related semantically is this button or link that I'm looking at, how related is that to my goal? Okay, and so if it's highly related, you might decide to click on it. If it's very low related, you keep going. So it keeps looking around, look, and it's got all this math under the hood that has all these utilities moving around a lot and saying, should I read the next thing? Should I click on the best thing so far? Or should I back up to a previous screen? And it finally decides to do something other than just reading. And in this case, it's deciding to click on that link. You know, this projector is not showing. There's actually text under here that I can see on my screen that I apologize that you can't see. I'm sorry. So we get quite good accuracy. Remember, I said you have to know what the accuracy is. Okay. Also remember, user testing has an accuracy as well. It's not 100% of the truth either, because you're taking, 10 people and you're trying to predict the whole population as well. People kind of tend to forget that sampling and experimentation also has an accuracy.
Well, you have no other. What's your gold standard? You got to compare.
Yes, yes, right. So the gold standard would be testing everyone, which is intractable. Well, right. That's right. Okay, but in 36 tasks, Cog2 Explorer correctly identified 93% of the easy tasks, where we were defining that as more than 95%, 95 or more percent of the people would finish it within 3 minutes, and the model would also finish it within 3 minutes of simulated time. Okay, and it identified 93% of the hard tasks, which we basically said, if less than 75% of your people can't do this task in 3 minutes, you've failed. Okay, this is bad. This is hard. And of course, your project would have to decide what your thresholds are, but this is what we did here. And so you always have false alarms and misses. So it missed only one hard task, which turns out to be 70% when you have 36 tasks. And it false alarmed on only 2 tasks, which is 9%. So you're not going fixing things, very many of them that actually weren't broken. Okay, and again, you'll have misses and false alarms on human testing as well. So this allows UI designers to focus on the things that are really bad. Go back and redesign those and preserve the things that are working for people. Again, this was a PhD thesis that was quite successful, and this is the vision. This hasn't been as researched as well as the hundreds of papers on that skilled performance predictions, but because it's relatively new. But this is work that is continuing at kind of a low level, but it is continuing. So we have been using this at IBM for a while. We have a paper here at ICSE, a 2011 paper that you can get to see these 5 different projects that used it in. I can have time to tell you about a couple of them. The first one is called PERCS, which is affectionately known at IBM as the Bidirectional Time Travel Project. Its more official name is the Productive, Easy-to-Use, Reliable Computing System, which was in response to a DARPA High Productivity Computing System initiative. And this was everything from new chip technology, new computer architecture, operating systems, compiler, and programming environments. And this is a DARPA slide. If you've ever seen a DARPA slide, this looks like a typical DARPA slide. I got this off DARPA's website. And the important part here for me is that it says that it has to speed up end-to-end performance by 10x, including skilled programmer performance, so human performance. Now, as a U.S. taxpayer, I am thrilled to tell you that they wrote the contract that IBM did not get its last increment of funds until they proved that they were 10x better. The U.S. taxpayer. As an IBMer, I'm unhappy they wrote it that way, because when was the last time you saw anything that got a 10x improvement for real? Okay? But I can also tell you they did get their money. But let's say, what the heck is with this bidirectional time travel? They're contracted to deliver 10x performance. 2002 was said to be the baseline. 2011 was the prototype delivery date. But in typical DARPA fashion, they didn't give them the baseline. Okay? So to get a 2002 baseline, you would have to travel backward in time and do empirical tests with programmers who understand 2002 technology. And even if you had the machines, the same machines, so you get the same system response time, the same systems, even if you could still get them to run in like 2010, 2009, you wouldn't have the people who only know that which had come up to 2002. So you do have to travel backward in time to get your empirical baseline. Then the proof has to be delivered the day that the prototype is delivered. So you have to travel forward in time to get people who now know how to use the system and are skilled at it, so you can compare them to the baseline. So the guy who was in charge of the usability of this, John Richards, kept saying, you know, if we could really deliver bidirectional time travel, DARPA would give us a lot more money. Okay? So this was okay for me because I said to John, hey, models can do that. Models can represent knowledge of people at any point in time. So we represented, I was still at CMU, he asked me to come for a sabbatical for a year to help them with this problem, and teach them how to do the modeling and do these sorts of proofs. So we represented both the old system and the new system in storyboards. And so again, we have the frames that represent what the system would look like and the transitions between them of what the person would have to do. Each one of those frames have widgets, have these hot spots on it with what you have to do, and you represent those. You can also have click, double click, system response time. You can put that in. How long does it take to do this? Then we demonstrated the task. We had a whole suite. They had about 30, more than that. I think they had eventually 100 tasks that they were doing it on. And this is just what I showed you before. And this is one of the early spreadsheets that we could share, and this is also published. And you can see the command line one was the old one, and the PDP Eclipse was the new one. And you can see they're getting better. They haven't gotten quite their 10x yet, but this was very early, and they did eventually get it. But more important, we could go into those visualizations and say, where are we getting this improvement from, so we can convince people that it's not just that we fudge the numbers, okay? So, and they wouldn't ever fudge them much. No, never. I'm not saying that at all. But it is a little more convincing to show them some of these timelines, okay? And we annotated them, and you can show a little more convincingly. So that's the one I can tell you the most about, because it was a government contract, and so a lot of it is public. So I can't tell you quite as much about some of the other IBM products, and of course we named them kind of nonsense names. One was called Do It. We called it Do It in the publication. And the important part about Do It was that the customers were saying, this is clunky, it's inefficient. Now, IBM sells to the enterprise, okay? IBM is supposed to be really efficient, so I don't like this kind of customer feedback, okay? Well, the developers attributed this to a problem with single sign-on. You had to stop and log in 16 times a day, okay? And so they said, well, we know where the problem is, it just hasn't gotten up on the priority list. So they did this modeling, and they did use it to see, is this hypothesis true? So we used screenshots of the existing systems to create the storyboards, and we could run the models, and then we could get our visualizations, and you could say, all right, what's happening here? The top one was IBM's, and it had all this sign-on stuff in the middle of your task. The competitor is on the bottom. Well, they start off the same, and then IBM throws you into this login screen. But then at the end, so this is the same pretty much as this one, okay? But here, IBM had another step that the models revealed. So the programmer's hypothesis was true, but it wasn't enough. Now, they had information, they had a way to display it that people could understand it. They stopped arguing because it wasn't just opinion anymore. They prioritized it, moved on. Let me tell you, the program manager was thrilled, okay, because it stopped this discussion between the usability folks and the developers about how high a priority is this, and how much is it going to take, and how much time would it really save. So this is what I just said. Okay, they were very, very pleased with how this could help them understand the problem better than they ever had, and find something new, and move on. So the next one that's interesting is something we call Portal, and there was a new company portal. It wasn't IBM, it was an IBM customer who asked IBM for help because they had put out this new portal. It's the type of thing where you're going into HR and you're finding stuff about your insurance or your benefit, stuff like that. And I don't actually know what the content of it was. Doesn't matter. Other people at IBM did this work. But their problem was that their beta testers were coming back and saying, this is a dog. Give us back our old system. This is terrible. Well, whose fault is it? Is it that new UI, and it's that UI people that's their fault, they have to redesign? Or is it something else? So what they did, and I can't show you the models on this, is that they went back, they did the models, they got these visualizations, and they did an interesting what-if game. They did it where they had measured the realistic system response time, was one way. And then they went in, because it's easy in a model, and they just removed all the system response time and made them all 0. And said, what if there was 0 system response time? So the realistic one was what the users were seeing. And the what-if one was, what if it takes 0 time to get all your information, all your database queries, everything comes back in 0 time? If that was now going to, and they compared it to the old one. Sorry, they did the old one. Okay, both ways. So if the comparison of the 0 system response time shows that it's faster than the old one with 0 system response time, then it's not the UI's fault, because the only thing it's doing is the UI. But if the new system with the system response time is slower than the old system with the system response time, that's the realistic situation, that one was slower. It's the database lookups. So they now could assign the right people to work on the problem. And so this was also, again, the project managers, the program managers, they love this tool because it helps them in so many ways. It helps stop arguments. They also found, if you go back to the 60 paper, it shows how they help communicate to customers as well as within the development team. And it helps understand who to assign to fix something. So again, it removes the opinion out of it and a lot of the finger pointing. So these were things that IBM found very useful. So again, we've been talking about predicting human behavior and proposed design. That was the original thing we were going to talk about, and that was originally what I wanted Cogtool to be able to do, just when you were doing design ideas. Well, if we look back at these projects, the ones that are turquoise, brighter, they were all actually evaluating existing code. And only the last one, which I didn't tell you anything about, was evaluating a proposed idea versus existing code. Existing code. Well, it seems kind of stupid to make a storyboard out of something that already runs. And that's what we were doing. We were taking screenshots of things that run, making these storyboards. So the obvious step is, can we automate the creation of Cogtool models when you have the running code? Now, you won't have your competitor's code, but you'll at least have your code if you're doing version N and version N+1 and all that sort of stuff. So we had a work with the University of Nebraska with a student there and a professor there that we reported at CHI in 2012, something called Cogtool Helper. So to be able to do kind of automatic model creation from existing code, we needed two capabilities. One is menu extraction. It had to go in and find the GUI. It's going to have to make the storyboard, right? And so it's going to have to actually know what is the size of widgets, buttons, menus, all this sort of stuff, what is their position, and what type are they? Because the type, is it a button, is it a menu, is it a menu item, is it a walking menu, is it a checkbox, is it a link? Those things are the magic that give you the proper placement of the mental operators. Their mental operators are tied to the type of widget, because in prior research, people pause differently with different types of widgets. And you also have to be able to replay tasks that will execute on it to get the path through. And these two things actually exist in research GUI testing tools. So as a proof of concept, we use a tool called Guitar that comes out of the University of Maryland that uses the Java APIs for accessibility to extract this information. Now, we had to modify it a little bit. It's also open source. And this is how Cogtool Helper relates to Cogtool. So we do a little setup first, and then we do a task construction where we're interested in capturing these tasks. You can also save them and import them later. Or you could write them by hand if you wanted to, but that makes it harder for a lot of people. That we then have saved as test cases, and we go into the GUI, the running code, extract this menus, all these, it's not just menus, it's all the widgets, but they call it menu extraction, because those are the hardest, because they're dynamic, okay? And then it replays the test that you're just going into the code and demonstrating it. You're just demonstrating it, okay, on the running code. And then it not only does exactly what you told it to do. So remember I showed you one where we did everything with keyboard, and the other one we did with mouse. Well, there could be lots of commutations of that. You could do part with the keyboard, part with the mouse. Okay, and this will then it will detect that you've gotten to the same place on the storyboard and do all the inference of different ways you could have gotten there. Okay, and then it makes an XML, which it throws into Cogtool. In Cogtool, you import it and you run it. Okay, this is what it looks like. You just have one little form to fill out. It's so easy. You tell it, where's your application? You tell it, where do you want to store the results? And you tell it, create a new task. It gives you a little form to fill out. What do you want to name it? What do you want to name the method? This is use menus or use toolbar. Okay, you could add other ways to do the task. You tell it to, well, you don't have a new one here. You just tell it to go. Okay, there's a go button there when it's in the right mode. And it opens up the application, and you do your task. And then you say, stop, I'm done. So it creates the storyboard, and it infers these steps. So you might demonstrate this red method and the black method, it's going to find these other ones that go back and forth across that as well.
Did you say
Yep.
it needed access to the source code of
No.
the application or just executable?
Just executable. Okay. So we did this. So here you can see. So like this is the type of storyboard. It makes a full storyboard. It's got all the menu items. It's got all where they go to. It gets pretty big. Okay, and then we put in 2 methods by hand and then inferred 6 more. Okay, and so it gets a lot of times. And okay, so this is the sort of thing the Cogtool helper does. Now, the next thing, we now have this doing things automatically, right? So the obvious next step is to do what we call human performance regression testing, because now it's kind of all automatic. So just like functional regression testing, where you have unit tests and stuff that you're going to automatically run every time you change the code to make sure you didn't screw it up, okay? You can do, it was doing semi-automatic creation of predictive human performance models, but we can do automatic ones. Let's see what else we need to be able to do that. Before we only needed 2 capabilities, the first 2 bullets, now we need 4. We're going to have to know more about the actual action of this thing. It's called an event flow graph. Guitar already does this. A lot of GUI testing tools and research do this sort of thing. And we need a test case generator that's going to traverse the graph that it makes and generate test cases. Again, we did a proof of concept using Guitar, and we have a paper at ICSE 2013 about this.
What's the connection to part of needing that accessibility API?
That's the mechanism they use to extract the menus, because the accessibility API lets someone with a screen reader do things.
You have to have written it in Java for that thing to work, is that correct?
Guitar has many different versions. So it has a Java version, it has Python as a C version, it has several different versions. It has a mobile iOS version and an Android version, but so it may use different, they get access to that in different ways. This is the one we used as our proof of concept. So you'd have to go to the Guitar website and find out all. Okay, good. A lot of them don't give the position and size. You have to be careful because Cogtool needs that for Fitts law. They give you it extracts a lot of commands, but not some of the things we need. But anyway, we can talk about that offline. Lots of different ways to do it. So there's a little difference between GUI regression testers and usability testers. So GUI regression testers want to find as many flaws as possible, the people, okay, and the systems. So, for instance, they literally will test something like hitting the delete key 4,000 times in a row just to see if it crashes the system. They want to find that, okay? And it takes virtually no time to do that in their GUI testing situation, so they just do that, okay? But usability testing, particularly we're testing for efficiency, we only want to test those things that people would actually do. And in this case, skilled people would actually do. So the GUI testers extract all the information in a graph to do all these things that people would never do, okay? But we can help that. And I have a picture on the next slide to show that. So regression testing, GUI regression testing really is, and very active research in software engineering for functional testing. So things may come up, new things may come up. James may know some things that have come up since we did this work, okay? But what we're going to do is whatever graph they come up with, we're going to prune that to do only those things that humans, in this case, skilled humans would do. So the way we did this was we wrote some rules that are sensible for skilled people. So for instance, an event that expands a widget, like a menu, a skilled person doesn't open a menu and not click on something. They open a menu because they know what they want to click on is in there. A novice can open a menu and look and decide not to go there, but a skilled person wouldn't. They would only go to the menus they want to use. So we have a rule that says, prune out everything that opens up a menu and closes it. Don't use that, okay? Or if a window is opened immediately and then immediately closed, that's not something someone would do. If they open a window, it's because they want to do something on it. So we pruned the big graph that the regression tester, so like here's the whole graph on a small task that that Guitar would extract, and we said, that's great for functional regression testing. We don't need all that, so we used our rules to prune it down to only that which skilled humans would be reasonably expected to do. Now, of course, you can override it. We can write rules that override things. There's special cases and all that sort of stuff. But now, with that previous graph of what happens of how you do Cogtool Helper, which was to use the system, okay, it used to be that you demonstrated them, but now we have a whole system that goes into the code, identifies all the widgets and actions, extracts these subgraphs, we write the rules, it generates the graph and prunes it, and comes out with test cases directly into that. So here's the difference. Originally, the human would generate a small number of test cases. Now we have this test case generator that does that. We did a proof of concept on 4 tasks in LibreOffice. We had 3 hypothetical versions, one that had menus only, one that had keyboard with shortcuts, menus and the keyboard shortcuts, and menus, the keyboard shortcuts, and toolbars. Okay, because LibreOffice we could change. So what you would currently do, if a human were doing Cogtool models, you would do 3 versions of Cogtool. One with the menus as much by hand, keyboard as much as possible, and toolbar as much as possible. You'd do 3, because that's all you could stand to do. And you'd say, oh, look, toolbars are better. Okay? But now, when we're doing automatic test case generation, we could do all of them. Okay? So we had 81 different ways of formatting text, of this formatting text command, with menus, keyboards, and toolbars, because it's all mixtures of those. We could run them all and see if we found any regressions, meaning it got slower. Okay? And so we did find a couple of regressions. So, you know, what does it really mean? We're not really sure yet, but here's what you would have done by hand, and here's what we get from doing it automatically. We now have a histogram. So you can see that the menus only stays in the same bin of time, no matter how you do it. Okay, it's basically using menus in a different order. Okay, but when you add the keyboard shortcuts, you can actually get a little slower. Mostly, your average is going to be higher. Better, faster. And then if you add the toolbar as well, you actually get a bimodal distribution. So we're not exactly sure what to do with this information yet, because we've never had this sort of thing before. It certainly has implications for training, or maybe automatic help or something, because you only realize the benefits of the toolbar if you use them as much as possible. If you use them once in a while, you don't get as much benefit. You know, so you might.
They're already at least as good as the other ones, right?
These are not as good as this one. These white ones.
So what do we care about? Number of seconds here? I mean, what's the?
Well, yeah. Well, we're talking about efficiency. So yes, the time to take a task.
They're all pretty much in this 11 to 14 range, right?
They are. Yes.
And so it looks like if I use toolbar, I get in that range in the worst case, but in the better case, I can.
Yes. Yes. So this is what we found so far in a research paper, in something that we weren't looking for the biggest dramatic example. We just did 4 things.
So
right?
Does this give you, let's say, 9 interesting cases to then maybe do a usability study and see if you get the same thing, or
I'm not sure.
What would you do with it?
What we would do with it next is do it on more systems and see if we can find things that are more dramatic. Because keystroke level models are good within 10%. So some of these are really not, we wouldn't necessarily think of them as really dependable. So this is an approach, and really, like I said, we don't quite know what to do with this information yet. but it's something we've never had before, and it's kind of opens up a new way of doing research with these type of models. So I don't know. Let's talk about it. Thinking. See, I can see the gears going there. So basically, with this, we could actually set it up pretty automatically to different versions. You go through a loop. At each new version, you do it again. Okay, this we could set up automatically to do this. And again, you can read about this in our ICSE paper in 2013. Okay. So what I hope to have convinced you of is that cognitive crash dummies actually can predict things, and that maybe human performance regression testing is on the horizon. We have demonstrated it as a proof of concept, and it could be a really cool thing to do. Well, if you care about, it's a joining of psychology. It's exactly what I want to do. I'm beating psychology into a form that engineers can use it. Software engineers think regression testing is cool. They don't have to touch people. Okay, to get using models, simulated people. I like simulated people. Okay, and it can all be done at a touch of a button. So I'm going to try to bring that together. And I am at the end. So, thanks.
So we have some questions.
Yep.
Thank you.
Yeah, sure.
Hi. So I was wondering if you have different parameters with one of different types of users. So.
Sure. So so the question is, do we have different parameters to model different types of users? Yes. Let me tell you a little secret about Cogtool. Okay. It's in GitHub. You can get the code, and there is a secret command. So anything you read about in a research paper about Cogtool actually is in the code. But we hide it because there's the released version that is the only one that we have good documentation for and examples, and is for the consumers to use. But if you go into preferences and select enable research commands, then you have all the power that is in any one of our research papers. And several of our research papers have looked at these sort of things of different parameters for different people. So for instance, we've done work with Tiffany Jastrzemski, who did, her PhD was in Florida, that does a lot of work with aging people. She's now at the Air Force. But we worked with her to model elderly people using cell phones. And so they're using cell phones in a bunch of different tasks. And if you set parameters differently in that underlying engine, you can make it old. Unfortunately, for people like me, it really means that cognitive think time goes up. Okay, we basically get slower as you get older. So that's one. Another one that we've done is we have worked with a blind person who uses JAWS, the screen reader, and we've done Cogtool models of him doing his, checking his financial information, stock prices in the morning, gets up every morning, checks his stock prices, and to find out where we could and couldn't do that. Turns out Actar doesn't hear fast enough. I mean, he literally was listening to at 900 words a minute, and when some people say they couldn't understand their data, it means they don't know what it means. We literally could not understand our data. It's just the recording we had was something we couldn't hear. We had to call him up and say, what did it say? And he had to tell it to us slowly. Okay, and so we've started doing that. I know that Dave Kiris, that was one of the other architectures that I talked about, is now making Epic hear better, doing more vertical for that. So that would change the parameters of how fast someone can hear. So we've done some of that, and you can read about it in our research papers. Yeah. Yep.
So you showed us how it works for like queries and how you can predict the models, but do you think it would work as well for like new hardware or for PCI interfaces?
Okay.
Could you like have it on that?
So the question is, does it work for new hardware, and what would you have to do to make that happen? So, so right now, the really easy tool works fine and accurately for things on a desktop, things on a laptop, and things that you tap on handhelds. And the guy in Russia who has done it on wall-size things. Okay, to add different sorts of gestures, and so we also have, you can work on graffiti, but nobody uses graffiti anymore. Okay, but you would have to add new gestures for hardware that would create new gestures. It does do hearing, and it does do vision already. Does not have any tactile interface. The hooks are there. So you could go into, you'd have to go into the Aptar code. You'd have to learn how to do Aptar. And I have done this sort of thing, like when I worked with Boeing, we had things that were reaching across the cockpit, you know, and so I added new operators for that. And so similarly, you would, you know, do gestures or whatever you were doing. You'd have to add it. So it's not out of the box ready to do that. It can do voice. It can speak, it can hear, it can see, it can do the things on tapping. It doesn't, we have workarounds for like flicking, but we have data on flicking, but we haven't had the resources to build it into the easy to use tool yet. But it's all open source, so if you want to help.
Do you envision it for brain-computer interaction?
For what human computer? Brain-computer interaction. I don't know why not. I think I'd need to know. It would just be another input, like, you know, just be another. Yeah, I think we could do it. I don't know. Okay. Yep.
So original GOMS models were sequential, I guess.
Yes.
And CPM GOMS it will be parallel. If I'm doing modeling, let's say multimodal interfaces, is this supported, or is that different type of underlying modeling?
Okay, so the question is, original GOMS models and keystroke level models as part of the GOMS family were all strictly sequential. You could only do one thing at a time. Whereas CPM GOMS models, which were a type of modeling that I created for my thesis, you could do things in parallel. This, what does this version do? Okay, so this version is closer to CPM GOMS for multimodal because it has, Aptar has, it's based on Aptar. And so Aptar has visual processors, auditory processors that act in parallel. Aptar does have a cognitive bottleneck, which again is a research area in psychology, but it's not stupid to say there's a cognitive bottleneck. And so if I go back to any one of these visualizations, quickly, not so quickly, come on back to a visualization. Here we go. So these little guys, some of them are a little 50 millisecond thought that controls the eyes that are then getting information in and bringing it back. Another one is controlling the hand. So if you were to look at this, you know, this purple is in parallel with this hand. So you could have auditory also in parallel, but there would be a little cognitive bottleneck both for getting the information in and doing stuff with it. And again, this is there a cognitive bottleneck is an open question in psychology. If you buy Aptar's version of that, which a lot of people do, it is set up to do that. So you could do multimodal. Yeah.
So from this timeline, it seems like the black box is the thinking black box.
Yeah. Yes.
How do you know? How do I know it's not cheating?
So the question is, the thinking platform, the thinking box seems to take the most time. How do we know I'm not cheating? Okay, one of the ways you can know we're not cheating with that is you can go to the 100 research papers that have made the model, collected the data, and compared them. Okay, it's not just me. There's researchers worldwide who have done that. Okay.
But my question is, let me clarify.
Yeah.
Like one interface is better than the other, and like more complex tasks take more thinking. So like, how do you adjust to that?
So if one interface, so we always are doing the same task on both interfaces. So a more complex task will have more stuff to do, okay? And there are some things built in. So for instance, when I was working with Boeing, the pilot task, they do a lot of information gathering, and they're not doing a lot of button pressing. But the way CogTool works is you can tell it, you can have a look at operator when the only purpose for looking at something is to get the information and make a decision about it, not just I'm looking at it because I have to go look at it to touch it. Okay, and what we would do, and what CogTool does, is it puts a think time after looking at something to do that processing. And so it is a black box, and if you have other data from what other information or studies that you have done, that is the one thing we made editable. So we said the average thinking time is 1.2 seconds from a lot of prior research. But if you have a decision-making process that you said, no, my people really take 5 minutes to make this decision, you could just type that right into the think time. So we knew that that was something that would be most amenable to wanting to change, or our users to want to change, so we made it easy to change. So we're not cheating, we're basing it on previous data, and something made a noise up here that I did not touch anything. Okay, and if it's wrong, if it seems wrong for what you're doing, we've made it easily editable. Okay.
We should probably wrap it there.
Okay.
Bonnie?
Thank you. Thanks very much.